Hello students, welcome to our discussion on steep slope profiles, which is continuation of the concept that we started in our last video. So we learned that we would say that a particular profile is steep or mild or critical based on if yn is greater than yc, yn is less than yc, and yn is equal to yc. When yn is equal to yc, we say that it's critical. When yn is less than yc, we say it is steep. And when normal depth of flow is greater than critical depth of flow, we say that it's a mild slope. We already covered the concepts related to mild slope in previous lecture, and in this video we will be focusing on steeper slopes. So if I plot the steeper slope, let us ignore S1, S2, S3 for a while. We would say that if this particular profile is steep, if our normal depth of flow is somewhere here, our critical depth of flow would be at greater height as per the definition of the steeper slope. Now in this case again we would have three regions where flow is possible. So in most of the cases we would be having flow through normals, but we could have some water in region 1 or profiles in region 2 or profiles in region 3. So let us look into these profiles, that what these profiles would look like, and we will see the practical cases when in which situations we will have profile 1, 2, 3 with help of an example of reservoir as well as a sluice gate. So if we focus on profile 1, what happens is that our governing equation still remains the same, that dy by dx equal to S naught minus SF 1 minus Froude square. Now if we are in region 1, that means that we are higher up the yn, and that definitely means that SF is less than S naught. Again you can refer to module E1 and E2 to understand why SF would be less than S naught, because flow depth is greater than critical depth. That would mean that slope of energy grade line would be lesser in comparison to the channel bed. That would mean that our numerator is going to have positive sign. Now if we are in region 1, that means that depth of flow is greater than critical depth. This is the boundary condition. Here it would be equal to critical depth, and anything above here it would be greater than critical depth. That would mean that our Froude number is going to be a positive number. So if Froude number is equal to 1 when we are exactly at critical depth, or as we go above, that is in region 1, it is going to be greater than critical depth. So we say that our denominator is also positive because Froude number is less than 1 as the flow is subcritical. So dy by dx turns out to be positive. That means that in case of S1 profile, dy by dx is positive. That means in direction of flow or depth of flow should rise. Now to look into the sign, whether it is going to be concave or whether it is going to be convex, we have to check the sign of d square y by dx square. Again, that is beyond the scope of this first introductory course that you are having in water resources engineering. But we have learned that for these steeper profiles, our d square y by dx square has opposite sign as of dy by dx. So if our dy by dx is positive, d square y by dx square is negative, that would mean this profile would be convex upwards. Let us extend the similar discussion to case 2. That is what would happen if our flow is happening somewhere in the region between y and yc, whether water would rise or it would fall. So if you again look at the same setup, here our depth of flow is again greater than if we are somewhere here, our depth of flow is greater than the yn. That would again mean that our SF is less than S naught. That means our numerator is going to be positive. However, now we are below YC. That means our flow is supercritical. That would mean our Froude number is greater than 1. And if Froude number is greater than 1, that would mean 1 minus any quantity greater than 1 should give us negative sign, and positive upon negative is equal to negative. That would mean that as we progress ahead in region S2, our flow depth should decrease. Finally, we apply the same discussion to dy by dx. Now in this region, our depth of flow is less than normal depth of flow. that would mean our SF is greater than S naught, and if SF is greater than S naught, the numerator is going to be negative. Our denominator is also going to be negative, because this entire region belongs to the supercritical flow or Froude number greater than 1, and if Froude number is greater than 1, that would mean that R for profile S3 dy by dx becomes minus divided by minus becomes positive. That means profile would rise in S3 zone. Again, we will come to the various real world scenarios that how this is applicable, but we have to understand that in this S2 no rising profiles are possible. These profiles would only be drawdowns. Whenever water is decreasing in the direction of flow, we call it as a drawdown, and S1 and S3 would be backwater profiles. Now, similar discussion we can extend to critical slope, but I will take a momentary pause here, because the two most commonly encountered slopes in real world are steep slope as well as milder slope, and that's why they deserve a special place into our discussions. Now, when we talk about critical slope, what happens with critical slope is that now we don't have three zones. Why? Because our yn coincides with yc, because that is by definition a critical slope, that is yn is equal to yc. So we only have zone 1 and zone 3 here, and zone 2 vanishes. Now in zone 1, our depth of flow is greater than the normal depth of flow. So we can clearly say that our numerator is positive. In zone 1, anywhere here, our depth of flow is greater than critical depth. Again, if you recall E versus Y curve, if Y is greater, that would mean that Froude number is less than 1, and hence denominator is again positive. So that would mean that in this case, in zone 1, our water depth should increase. Then comes the zone 3. What happens in zone 3? Our SF is less than or our SF is greater than S naught. SF is greater than S naught. Why? Because our depth of flows are lesser than normal depth of flow, and that would mean SF should be higher in comparison to S naught. Our Froude number in this case is greater than 1. Why? Because we are below the critical depth of flow. So we are somewhere here where Froude number is greater than 1. That would mean our denominator is negative. As a result of which our next sign is positive. That would mean in zone 3 our water profile should again rise. So we can extend the same discussions to horizontal and adverse slope, and again in horizontal slope, that means that we have perfectly leveled ground. That would mean that no normal depth of flow is possible. So yn would tend to infinity. Similarly, in case of adverse slope, yn would tend to infinity. And applying the same analogy here, that checking the sign of dy by dx as function of S naught minus SF, 1 minus FR square, and same equation here, S naught minus SF, 1 minus FR square, we can check whether it is going to increase and decrease, and I leave this exercise to the readers that how you can develop these profiles. Now, there is one thing that I want to attract attention to, is that what are the asymptotical behavior at the endpoints here. So for example, if we take the case of profile S2, now at the starting point, what you see here is that at point that I am highlighting right now, our Froude number would tend to 1, because this is by definition the critical flow, because the depth of flow is yc. If our denominator is equal to 1, or Froude number is equal to 1, our denominator tends to 0. If our denominator tends to 0, that would mean that at that local point, dy by dx is going to be infinity. And that's where we say that asymptotically, we should have the infinite slope here or a perpendicular line here. That means the profile of water will fall suddenly, and then it would try to adjust to the positive values or the negative values of dy by dx that we obtain in case of S2 and positive values that we obtain in case of S1. But the key takeaway here is that wherever these water profiles meet the critical depth of flow, we have a true asymptotic behavior with infinite slope. Similarly, when we talk about what happens when our water profile approaches normal depth, We know that when water profile approaches normal depth, our S naught becomes equal to SF. That would mean that in case of dy by dx, the numerator would become 0, and that means that at normal depth, our water profile becomes parallel to the normal depth of flow. And that is how we can analyze the asymptotic behaviors, that what would happen to the profile or to the tangent of water profiles at various boundary conditions. Now comes the most awaited question, that how these profiles are going to look like in real world, or why these profiles will develop. So let us try to understand this with help of an example of a mild slope. We have a mild slope here, and this is flowing peacefully, uniformly throughout the section. So in case if it is a uniform flow, what we would have here, we would have our YC here and we would have our YN here, because it's the case of mild bed. If that is the case, this is YC and this is YN, and by definition YN is greater than YC in case of M profile or M type of channel sections. Now suddenly, not suddenly I would say, because we are talking about gradually varied flow, let us say that this is a long channel of hundreds of kilometers and somewhere we have a gate. So this gate is designed to stop the water, and you can think of it that we are trying to create a reservoir here. Now what would happen? This reservoir would have some water level here, because that's the purpose, and water should rise. So you could clearly see that water initially was flowing at this depth. So water initially was flowing here, and suddenly it has to adjust to the water that this reservoir would have. And clearly you would see that initially it was at Yn. Now depth of water should increase, and by definition of M1 profile, dy by dx should be greater than 0. That means that since M1 profiles allow dy by dx to be greater than 0, a gradually varying profile is possible in this case. Now when this gate is opened, initially let us say this gate was completely closed and we push it upwards, so that now it is in open position and water will try to escape from here. Let us try to see what happens. Now the streamline of water that is trying to escape would be somewhere here. Now you clearly see that if this was region 1, this was region 2 and this was region 3. Ultimately it will try to reach Yn. So what it would do, if you recall that in case of Y3 or the third profile that we have, water will try to rise, because that's what we discussed when we were talking about these rising profiles, that in case of the milder slope, Y3 water will try to rise. But at the end, our river would be flowing uniformly, because our channel would be flowing uniformly. But now when it has to cross YC, what would happen? It would have to produce a hydraulic jump, because ultimately downstream it would try to join or match its natural slope, because this natural slope would correspond to the minimum energy of flow. And that is how we also produce hydraulic jump in controlled setup. That is, we provide the channel bed in a way that is normal depth is greater than YC, and it is also greater than the depth of flow at which we are leaving the water, and hence when the water transits from point A to point C, it will cross YC, ultimately resulting in production of hydraulic jump, resulting in dissipation of energy. And that's what we wanted here. We wanted to dissipate some energy so that the kinetic energy component of flowing water gets minimized, and ultimately in from region 1 and region 2 it will go here. And here we will say that although this profile is going to be gradually varying, in M2 we have nothing like rising profiles. Again, going back to the figure that we had, in region 2 we cannot have a rising water, it has to be a drawdown. So we say that there is not a possibility of having a gradually varying flow in region 2. So this entire area that I am highlighting now would be marked by rapid flow. This area would be having gradual flow. After formation of this hydraulic jump, this water may go up and it may continue flowing here. or after some rapid transition, it may join the natural slope which happens to be yn. So this is one example where we would have transitions from y normal depth to m1. This would be m1. From m1 we would have m3. m2 here is not possible. That's why this would be a case of rapidly varying flow. Now we can extend the same discussion that instead of milder, if we have a steeper slope, then we would also have the same behavior, but in this case we know that curvature would get inverted, but still water will try to rise. Similarly, curvature would get inverted here, and in this case yc would be less than yn, so it may happen that hydraulic jump may not form because our normal depth of flow is lesser than critical depth of flow, and hence we would be able to transit this water without formation of hydraulic jump. So what I meant is that, let us say that if we have a case of steeper slope here and we put the same gate here, our normal depth of flow would be somewhere here. This is our critical depth of flow, and this is normal depth of flow yn. Now our water reservoir is somewhere here. Our normal depth was flowing here because now this is a steeper channel, and in case of steeper channel we learned that our yc is going to be greater than yn. Now water is flowing here and suddenly it wants to take a jump. So what it has to do, it has to cross the line of y3. So from here going upwards, we know that in case of this would be zone 1, this would be zone 2, zone 3. In zone 2, no upward profile is possible. That means it has to be rapidly varying flow. Once it crosses region 2, it would enter into region 1. And in region 1, we learned that S1 profile would exist with dy by dx greater than 0, and it would be convex upwards. That means if this is rapidly varying flow, here we would have gradually varying flow with profile S1. And since, as we learned, in case of dy by dx would be negative if we are talking about steeper slopes and flow happening in region 2, we really cannot have a physically plausible explanation why this flow can be gradually. So there has to be a rapid varying flow, and this becomes a hydraulic jump. Now when this gate is opened, water would be released from here. It ultimately wants to join the normal depth of flow, and now it doesn't have to cross the critical depth. So what it will do, it will peacefully take the profile S1 without formation of hydraulic jump. So we will have formation of hydraulic jump upstream in case of steeper slopes, and downstream in case of the milder slopes. And in case of steeper slope, downstream transitions would be smoother, whereas upstream transitions are going to be like in form of a rapid varying flow. Now with these two examples, you can really extend this discussion to all other cases. And in next lecture, we will extend our discussion into that what happens if there is transition in slopes. For example, there is a steep slope followed by a steeper slope, or there is a mild slope followed by a steeper slope. So if this is a mild slope and this is a steep slope, how these water profiles are going to look like? Is it water going to rise up? It is going to go down? We don't know how it is going to look like, which would be topic of our next discussion. Thank you.